morning, afternoon, or 2 a.m. Whenever you're watching this video, I hope you're doing well. This lesson will be on the star life cycle, which we started with this week, but this video is just to kind of help condense everything. I want to simplify the steps for you so it's really clear, and I still suggest that you watch the videos that were provided to you in your first assignment of the week. The objectives for this lesson, or what you should be able to get out of this lesson, is 1. List the steps of the star life cycle for small stars and massive stars, and compare the elements that are formed in massive stars and smaller stars. And let's just get started. So first, stars begin as a cloud of hydrogen atoms called a nebula. This is a really, really big cloud of just atoms floating around. These started to pop up after the Big Bang and after atoms formed, all of that. The size of the nebula will determine the life of the star. It's pretty straightforward. If you have a small nebula, you will form small stars, and if there's a massive nebula, it will form massive stars. Gravitational attraction will cause the hydrogen atoms to condense together. So once there's enough hydrogen atoms just around each other, they'll start to gravitate towards each other, getting closer and closer and closer. They're also getting hotter and hotter until they form a protostar. A protostar is a baby star made of extremely hot hydrogen atoms. They're actually going to form a plasma. After this happens, we are at a small main sequence star. Our sun is a good example of a small main sequence star. When the temperature is high enough in the protostar, nuclear fusion can begin. Nuclear fusion is the process of hydrogen atoms coming together to form helium. This kind of reaction doesn't just happen on Earth typically, because there's not enough energy just on Earth to make that happen. But in the core of a protostar, when it becomes a main sequence star, there is enough heat and pressure to force those hydrogen atoms together until they form a new atom. Helium will be first. Nuclear fusion will occur in the core as long as there is enough hydrogen to fuse. This is the phase our sun is right now. It's kind of weird to think that our sun is just a small star, because it's so big and it provides us on Earth with all the energy we need to do all the things we do, but really it's just a young, small star. This rest of the sequence is going to show us what will happen to our sun within the next billions of years. After the main sequence, the star will enter the red giant phase. I like this picture because it shows the size difference. The sun would blow up to something this size, a red giant. The core of the main sequence stars, so this one, the core of this main sequence star will become hotter and more dense as fusion goes on. Eventually, the increasing heat and pressure causes a helium flash, and that's basically an explosion. This will cause the star to expand, forming a red giant. When this happens to our sun, it will completely burn up Mercury, Venus, and possibly Earth. The good news is there's no way we will live long enough to see that happen. Depending on the size of the red giant, helium will fuse to form heavier elements such as carbon, nitrogen, and oxygen. For our smaller stars, that's as far as they will go. When the star eventually dies, it will form what we call a white dwarf. The red giant will explode, leaving a white dwarf behind. This is not a real picture, it's just a size comparison to show that the sun, not the sun, but the star went from being this size, like our sun as we know it, it blows up to this red giant, like this, and then it condenses all the way back down to the size of the Earth, which is so much smaller than the sun. So all this matter is just packed in there. During this stage, all fusion stops. There's just no more material to fuse. And the star is left to release heat and light energy. And it will just sit there releasing all that leftover heat and light. After billions of years, it will run out of heat and light energy, and it will become a black dwarf, which is also known as leftover star parts. There are actually no black dwarfs yet in this universe because this universe has not existed long enough for that to happen. And that's it. That's all for our smaller stars. For our massive stars, things look a little bit different. Massive stars begin with massive nebulas, so they'll also go through the main sequence stage and a red giant phase. You'll also notice that our massive stars in the main sequence phase are bright blue and not red or yellow like our sun. Oh, see, I'm ahead of the game. Smaller stars will be red or yellow. So here's a red dwarf, here's a yellow dwarf like our sun, here's a blue dwarf, and then here is just a massive, like this blue outline is a massive star here. I can't quite make out what it says. Massive stars are going to be at least 9 times greater than the size of our sun. So massive stars have a super red giant phase instead of a red giant phase, but it's similar to the red giant phase we saw before. In the cores of massive stars, heavier elements can be formed, like neon, silicon, and iron. Iron is the heaviest element that can be formed in the core of a star. So once we get to iron, that's it. Iron does not release energy when it is fusing, so the fusion just stops there. When that fusion material runs out, another explosion will occur. This explosion is called a supernova. A supernova happens when the core of a giant star collapses. And that's this picture on the right. This causes a huge explosion and release of light energy. Turns out all the energy that the star released over its lifetime would just get exploded and thrown out in a single second. The only place heavier elements than iron can be formed naturally are in a supernova explosion. So this is where we would find bismuth, gold, silver, and platinum. That's where it came from upon this explosion. That's how those elements ended up on Earth. That's why they're so rare and valuable. It literally took a star to die twice to make these elements. And then suddenly diamond seems so invaluable because it's just carbon. If you're going to propose to someone, I say propose to them with a bismuth ring. See how that works out for you. After the death of a massive star, there's 2 options we have here. On the left side, we have a neutron star. If it's a smaller massive star, this is the path it will take. A neutron star is made of all the star material that didn't explode away, and it gets condensed into the space the size of a small city, which is just crazy, crazy dense. You see, this is like our sun, and you know Earth is so much smaller than our sun, even smaller than a red dwarf. Imagine this massive, massive sun collapsing into space the size of Denver, Colorado. That is just insane. They're very dense, and the physics gets super weird inside these neutron stars. I highly suggest you watch the video that was posted earlier this week on that. If the star is even bigger, though, and it goes through a supernova explosion, and it's 20 times the size of our sun, it will collapse into a black hole. In a black hole, all star matter is condensed to a single point. So smaller than Denver, Colorado for sure. Imagine that giant, giant, massive sun, once again, collapsing into one single point with no volume. It doesn't make sense because it's like trying to divide a number by 0. It's just mathematically, it seems like it's impossible, and yet they exist. And that's why they're so scary and weird, and we know so little about it. Even light cannot escape a black hole. Once it enters this event horizon, which is what we're seeing here, it becomes part of that singularity. It's just gone. And it's just crazy. I can sit and think about black holes all day. I want to show you this HR diagram here. This is basically just showing our main sequence stars and the fate they will go through. So if a star is super, super massive in its main sequence, it will become a supergiant, just like this. And if it's smaller, they'll make smaller red giants, and eventually they will become white dwarfs. That's all that this is showing. And finally, I wanted to show you this diagram here. It just shows the life cycles of different stars, and this one is a lot more complicated than what we just went over. You don't need to worry about knowing all of these little bits and pieces, okay? Just the ones I showed you. But you'll see there are stars that are even smaller than our sun, and they won't even make it to this main sequence. They will make a brown dwarf, which is similar to just a really hot planet. And then you'll see there's different types of supernovas. You don't need to know all this, but I did want to show you this picture just so you had an example of what I'm looking for the star life cycle diagram assignment. Let me know if you have any questions about that. And that is all. So I hope that was interesting for you and that you learned something new. If you need any help, just let me know, and you know where to find me.